Better Buildings for Humans is powered by Advanced Glazings, makers of the Solera line of products. Solera is the leading glass glazing made specifically for architectural daylighting and with extreme insulation performance. Learn more at advancedglazings.com.
Hello, and welcome to this week's episode of Better Buildings for Humans. This is the podcast where we look at the impact that the built environment has on our health, our wellness, our productivity, our general joy of being alive. And of course, we have to talk about sustainable issues as well. Today, I have Dorit Aviv from the University of Pennsylvania. Welcome to the show, Dorit.
Hi, thank you for having me.
Dorit and I have been talking for a long time, trying to get the coordination and the timing to be able to finally speak. And I'm so excited to finally have this conversation. Dorit, let's start, like I always do, let's start by learning a little bit about you. Tell us about your career path, what led you to becoming an architect and become a professor of architecture at University of Pennsylvania, and of course, the founding of the Thermal Architecture Lab as well.
Sure. So I studied architecture at the Cooper Union and then at Princeton, and actually practiced as a designer in design firms, in architecture firms for quite a while. And I got my architecture license, etc. And then during my thesis, my master thesis at Princeton, is really when I started becoming fascinated by the relationship between thermodynamics and design. By the way, I had an amazing teaching team for that thesis. I had Liz Dealer, Stan Allen, Forrest Meggers, were all teaching me together and advising me. But anyway, that's when this fascination started of understanding how to design with thermodynamics. So for my master's thesis, I developed a roof typology for self-cooling in hot desert climate. And after I finished my degree, I got a Tides Foundation grant to further work on this and actually develop a prototype and build it and test it. And that became the foundation for my PhD dissertation, where I later did at Princeton. Then I joined Penn in 2018. And Penn is really a special place for my split personality of a designer and a researcher, because it has a PhD program in architecture, and it also has, on top of their Masters of Architecture program, they also have a post-professional program in environmental building design that was founded by Bill Bram. And there I get to teach design studios, but there are also, studios where they're kind of a research laboratory too, where we look at what we call bioclimatic design, how to design buildings within their environment in a way that adapts to the climate that they're in. And that's where I get in my teaching to really explore these relationships that I'm interested in. And then in 2020, I founded my lab, the Thermal Architecture Lab, as part of the Weizmann School of Design at Penn. And there we get to build prototypes, full-scale prototypes in a fabrication lab. We have robotic fabrication. We work on IoT sensors. We also have a big climate chamber where we can test our prototypes to see how they act in real climate. And we have an outdoor space to study their response to solar exposure. This is all located at a small campus off the main Penn campus. It's called Pennovation. That was formerly an industrial site that Penn invested in to become a research and entrepreneurship hub. The work that we've been doing has been funded by both like federal agencies like Department of Energy and the National Park Service, but also we've had a lot of industry collaborations with companies like Microsoft, like Ripple, like Armstrong World Industries. And I'm very lucky and fortunate to also have a growing body of researchers working with me at the lab, mainly PhD and master's students that are really wonderful, and they're really the ones that are driving the work there.
Oh, fantastic. All right. We are definitely going to circle back a little bit later on the full-scale models that you mentioned. I definitely want to talk about that. First, let's talk about the Thermal Architecture Lab. All right. According to the website, and I'm going to read it right off the thermal-architecture.org, the lab focuses on the intersection between thermodynamics, architectural design, and material science. Can you help us understand how that plays out and give us some examples of the lab's primary areas of research?
Sure. So if you think about it, what is really architectural design? In the end, it boils down to a set of decisions that you make about how to combine materials and forms. And every such a decision, or every such a combination is going to have implications. It's going to have thermodynamic implications. What do I mean? For example, when you put up a wall, or you pave a pavement. The materials you're going to choose, whether it's concrete or a wooden wall, or whether you coat it with a reflective material, that's all going to affect the way it's going to absorb heat from the sun or reflect it. It's going to affect the way that it shades the environment behind it. It's going to affect the thermal storage within the material. If you change the angle, that's going to change everything as well. So every decision we make is either going to instigate or delay some thermodynamic process. Maybe it's easiest if I give you an example for my work. So going back to those projects that I mentioned. So we have recently a Holcim Award, which is an international award for sustainable design for an adaptive cooling chimney for desert climates. It actually kind of grew out of my master's thesis, and then in collaboration with University of Arizona and with Princeton, and this was also funded by Microsoft partially. We built a full-scale prototype of it, and we actually embedded hydrogel membrane at the top of a chimney to create a surface where you get evaporative cooling. That evaporative cooling at the top of the chimney with hydrogel is this material that absorbs a lot of water. It holds water in it. So essentially you have a constantly wet surface and you can shape it. It's like shaping water into a specific surface and form. That hydrogel membrane that was embedded at the very top of the chimney, acting as a wet surface, would wet the air. The water in the hydrogel would evaporate into the air. And then that would create a downdraft cycle where the air that's coming against the wet surface absorbs humidity from it, gets cooler, and drops down, because just like hot air rises, then colder air drops down. So you get this cycle of fresh air coming into the building, and all you're using is this material with a specific form that holds water in it. On top of that, the skin of the chimney was paved with these liquids that were coated with a special coating that reflects solar radiation but allows for radiation into the night sky. So you get this additional cooling during nighttime from the skin of the chimney. So this was like a dual cooling action that's happening, and it's all driven by the surface, by the form, by the materials that you coat or that you embed into this. So that's what I mean, I guess, when I speak about this relationship between material science and architecture. And I also love to collaborate with the material science department in engineering. In the engineering school at Penn, we do a lot of projects together where we explore how these novel applications of materials can change the way that buildings are built.
Manage the connection between building occupants and the outside world using Solera translucent glass. Learn more at advancedglazings.com.
Do you think you'll be able, or somebody will be able to commercialize that hydrogel? Like, will it be reasonably cost effective? Will it be easy to install? Because it sounds like a brilliant way to do this.
This is a great question. There's a lot of challenges with hydrogel. It is a commercial product in the sense that, you can actually buy it commercially already. To make it integrated into buildings and perform over time is a challenge we're working on, because, when it is full of water, it swells and then it shrinks down as it dries. And you need to make sure that it has the mechanical properties to regenerate without breaking, etc. So there are definitely outdoor commercial hydrogels. They're actually used in many products because it's essentially like a material that just holds water. But the type that you can really work at scale, the scale of the building, is something we're still definitely in development.
Cool. Well, I'm going to be watching that for sure. All right, let's talk about the large scale models now. This is exciting. So, a lot of performance research is based on modeling, right? But you are working on actual full scale prototypes in some of your research. Can you explain why and what you achieve with these full-scale construction projects?
Sure. So, in the example that I just gave you with the adaptive roof chimney, we modeled it, of course, and I mean, we made an analytical model to predict how much cooling we're going to get out of how much water, with what scale of this, what is the right form. But in order to really validate these assumptions and actually, understand how this is working, because you're using so many things that are unknowns, you're using new materials, you're using forms that you haven't, that are not non-standard. And also it's within, you want to see how it functions within a specific climate. So we actually built this, it was like a 13-foot tall chimney, and we put it on the roof of a building in Arizona, in Tucson, Arizona, where we could actually test it in desert climate and see how it functions. Now, there's also like a big problem. You can do CFD modeling for sure, but you can't build small models when you're studying thermodynamics or fluid mechanics and then expect them to actually function the way the full scale would. So it makes this field really interesting, because if you're going to build a prototype, a lot of time you're really forced into a full scale one if you really want to get meaningful results out of it.
In the Tenopy project, you work directly with community members to test a structure, right? Can you talk about that experience?
Sure. So maybe I'll explain what the Tenopy project was a little bit. This is something we did this past summer. It's a collaborative project with the Penn School of Nursing and School of Engineering, and together also with a community organization called North 10, that is a community organization within the Hunting Park East Tioga neighborhood in North Philadelphia. And this neighborhood specifically suffers from the heat island effect. Now, just in 2 sentences to summarize what the heat island effect is, it's this phenomenon that urban areas are hotter than their surroundings. And there are different reasons for that. It's basically the way we build cities with heat absorbing materials like concrete and asphalt. It's the fact that you have less vegetation. It's the fact that you're building the form of the city actually traps heat, because you're making these urban canyons that essentially trap heat from the sun and also don't let enough wind go into them. So you end up with hotter cities, but within the city, you also get neighborhoods where this is more extreme, because there's much less trees, less vegetation, less shading, and you end up with neighborhoods that are more vulnerable to heat waves. And those tend to be also communities that already are vulnerable to other socioeconomic conditions. So it really exacerbates existing inequalities in urban areas. And so we were working with the North 10 organization to think about solutions to the heat island effect there specifically. And we came up with this idea of an urban cooling shelter that is like a bus stop where you can sit in the street and be shaded and cooled. And what we did was, how do you do this out in the street with open air, where normally you would think like you have to put people into like closed buildings with air conditioner to give them cooling shelters. That's like actually what the most common idea of what a cooling shelter is right now, is a building that's already air conditioned and people can go in there during heat waves. We wanted to do something else, something in the street, in the open air. So we actually provided cooling through a cooling bench. So you're sitting on the bench and you're being cooled by the surface of the bench rather than by the air around you. And also we put in radiant cooling panels that you can stand next to. You don't even have to touch them and they cool you. All of that is obviously shaded so that you don't get the heat of the sun. The heat prevention from the sun is very important. And all of that was also solar powered. So we were not relying on any external power source, which is, this is the type of resilience you actually need for heat waves events where a lot of time the grid fails. So when you have a lot of intense solar radiation, it's actually when you need a lot of cooling, and that's when you can power everything with solar panels that are on top of the roof that's shading you. And so This was just kind of an explanation of what the project is and what it tried to address. But the important thing about building a full-scale prototype, other than testing for the first time this combination of technologies and their impact on the human body for cooling, was also the fact that we could actually build it on the site and get the community to participate and give us feedback. So, without a full-scale prototype, I mean, I could model this and say this is a great solution, but until I actually test it with community members that are suffering from heat and are telling me this is great, or this needs improvement, or this is what I would like to have, I don't know if this is a real solution or not. So it was really a special opportunity.
I have to ask, what did the community say? What was the feedback from the people who tried it?
We did surveys and we're analyzing the results, but overall, people were really excited about it and really happy with it. I think this experience we did a testing during like a really hot day when we got the survey, hot and humid, which is like really where it becomes dangerous for people. So, that transition from being outside in the sun into sitting on a cooled bench or standing next to a radiant panel and being shaded was definitely a pleasant experience. And a community member even compared this to what she's experienced on the mountains in Peru, which was really interesting. So, I think part of it was the fact that it wasn't just putting you into an air-conditioned building, but actually you're in the city, you're in your street, but you get cool and you can see people around you, you can see the street, you can see what's going on, but you're being cooled at the same time. And I think that made a very nice impact.
Very good. All right. I want to change to, well, we're going to stay on cooling, but you wrote an interesting article for American Scientific, and congratulations, in 2021 called A Better Way to Cool Ourselves. If you've listened to any of the other episodes of this show, I love exploring the trade-offs between, energy, sustainability, and human comfort and health. So we're going down that road for sure. So here's a quote from the article. If we continue to conform with the current building cooling paradigm, the health of occupants and a building's energy efficiency will remain competing factors. I love conversations about the competing factors. Can we take a moment and make sure everyone understands why health of occupant and building energy efficiency are competing factors?
Sure. So this has to do with the way we've been designing buildings, basically since air conditioning and the central air systems became the norm. So the way that most buildings are built, buildings that have central air systems, is that they are thought of as like a closed system, a closed box. If you have windows, a lot of times they're not operable even, or you're not supposed to open them because you're relying on mechanical ventilation to provide you with air for breathing. At the same time, that air that is circulated through the mechanical system has to be preheated or pre-cooled to be within what is considered like comfortable for people, right? So there's an air handling unit where the fresh air comes in, and then it's preheated, pre-cooled, whatever it needs to be to, depending on the external climate, then it goes into the building through the ducts and the plenum spaces, etc., and shafts. So what happened during the energy crisis in the 70s and into the 80s is that pre-cooling or preheating all these volumes of air that you need to go into the building became an issue. And so engineers started saving on fresh air and started recirculating air in buildings. So you mix the fresh air that's coming in with recirculated air that's captured from the building. And then that all happens in the air handling unit and then being sent into the building. So you're saving a lot of energy because you're getting air that's already hot or already cold to what you need it to be, instead of all of it needing to be preheated or pre-cooled. Now, then after a while, people realized there's a sick building syndrome and people are getting sick in buildings. Then there started to be these new standards about how much fresh air you have to provide to people. But during COVID, it became clear that buildings are sites of infections. and that air is recirculating in a closed system from people that are sick, that's not a good idea. So then the international engineering associations of heating, cooling, and ventilations, they came up with announcements to go to 100% fresh air instead of mixing the air. But then we did a study, actually during COVID as well, to see what are the implications for energy of that. So the standard before COVID was that only about 20% of the air you're breathing in a building is actually fresh air. So to go to 100% fresh air, that could be 200% more energy consumption. So this is what I mean when I say we are in this, we're trapped in this dichotomy between energy savings and air quality and health. And this is because of the way we build buildings, where we rely on the same source to provide us both with air quality and with, comfortable temperatures, which is the air handling unit, the air that we're pushing into the building. We cannot open the windows in such a building because we're also compromising by that the energy of the building, because you're getting in unconditioned air. So, you're trapped in this paradigm. And if we want to change this, we actually need to think about, can we separate air for breathing, for air quality, for health, from our cooling and heating systems? And that's what radiant systems can do. So that's what the article is about, and specifically about the research we did to expand radiant systems to climate zones that couldn't handle them before. And I can go into that more now, or if you want to follow up with another question.
You know what? I want to talk about this just a little bit more. I've had several conversations recently about radiant systems, and when I talk to building scientists, there's a lot of excitement. But when I go out to, the practitioners, the day-to-day people, radiant systems don't come up very much anymore. These days, it's heat pumps, certainly for the residential world. What's happening? Let's talk a little bit more, if you don't mind. Let's talk about how the things that are stopping the adoption, a broader adoption of radiant systems. What's getting in the way?
This is a great question. We've been asked that specifically when we published that article. And so actually, together with my colleague at the University of British Columbia, Adam Rizanek, we actually collected a forum of experts, international forum of experts, to answer exactly that question of what are the barriers for adoption of alternative cooling systems. And it's a complex, there is no easy answer, except for it's a combination of things that are, none of them are technological. On the technology side, we have market ready products. It's really things that have to do with social, economical, cultural issues, where we're really kind of trapped into thinking about air conditioners as a single solution to cooling. People don't really think about cooling separately from air conditioners, and that's entrenched in things like our building codes, where to comply with building codes, a lot of time you really would have to make an effort to do it with a system that's not an air-based system. It's also not encouraged to try these other technologies through financial incentives, policy. Any new technology is going to have an issue with, like, how many people in the market know how to install it, how to actually work with it. And if you don't give people incentives to try it out, they're going to avoid risk, because this is a system that's not as widely used. So there's that. And then I think people also expect, especially in the United States, we've been used to air conditioning or air conditioners for so long. We are so used to thinking that we're going to step into a building and feel that effect of the cold air on us, that people forgot that they can actually wear shorter clothes or change clothes during the day, or adapt their own behavior. So there's also this expectation for like one form of cooling, and there's like less, I would say, like openness to being outside of what you'd call like your comfort zone expectations. That's also a part of society. So I think it's a combination of people not necessarily knowing about the technologies, not necessarily having the right contractors or engineers that can actually design these systems for them, And then there's really, we need policy too. We need incentives and we need building codes and standards to change to actually push this forward.
Do you want to bring lots of healthy, beautiful natural light in your building and still meet energy codes? Try Solera from Advanced Glazings. Learn more at advancedglazings.com.
We could do probably 2 or 3 episodes just on this topic alone, and we might. But for now, let's move on. I mean, buildings are complex systems, and there are several, of these sorts of trade-offs. We talked about the trade-off between energy and air quality. Are there other competing environmental factors that you're coming across in your research?
Yeah, so one thing that's really coming to the forefront right now is the issue of embodied carbon. And so you and I have just been talking about the energy takes to heat and cool buildings, which is part of what we call operational energy. And that translates into operational carbon. If you think about the fossil fuels that are needed to power those systems. But there's also the embodied carbon of buildings. And now this is maybe something that others on this podcast have brought up, but the building sector is the largest consumer of energy, or with the highest energy related global greenhouse gas emissions, more than industry and more than transportation. So that is huge. And if we can affect that, we can make an impact on a global scale. Any savings on carbon that we can do in buildings. But what is that made out of? It's made out of operational carbon, which is the energy it takes to operate buildings, mainly heating and cooling, other things like lighting, equipment, etc., but mainly heating and cooling. And then it's also the energy and emissions that have to do with the construction, with the materials that go into the building, with transportation of the materials, etc. And because there's this, in the future, it's projected that the operational carbon will be reduced because our systems are being changed to renewable systems, because we're trying to electrify buildings. This has to do with like what you mentioned about working on heat pumps. But so it's predicted that in many places, operational carbon would be reduced, while embodied carbon will become even more important than it is already. So how do you optimize both is not so easy. This is kind of something I came across in my research, and this is a trade-off that I think we need to be aware of. I'll give you like one example that's just like very common example is that when you think about like, what do I design with like a triple glazed window, it's better for operational carbon because you're going to have less heat loss. But if you start multiplying that, you're getting like all these additional layers of glass. That's a lot of embodied carbon. In my research, I'm currently collaborating with, in my department, Masuda Kaparzadeh, who is a structural engineer and designer, and with material scientist Shu Yang. And we're working with the Department of Energy and with other collaborators on developing carbon absorbing concrete for building structures. Now, concrete is huge when we talk about like this global scale of emissions. If you can actually reduce the embodied carbon of concrete, that's going to have a big impact. But what we discovered is that as you're increasing these properties of concrete that absorb carbon, you are also changing its thermal properties, and then it acts less well as thermal mass, which is one of the best things about concrete in buildings, where it actually helps regulate internal temperatures and really bring down your need for heating and cooling. So how do you decide which one is more important? There's not an easy answer for that. And it's, a lot of it has to do with like understanding the life cycle of building, how long this building is going to last, and how much of it is going to be impacted by its initial like material construction, which is embodied carbon, and then how much of it is going to be impacted by its operation during life cycle. There's no clear answer of like go this way, but this is why it's interesting in research right now, where you really have to start considering both, and you can't just go and optimize one or another. Carbon on the whole is eventually your constraint.
It certainly feels like the pendulum is swinging towards a greater emphasis on embodied carbon these days, which is interesting. I'm not really sure. By times, I think we're making some bad decisions on that. But how do you feel about that? Do you agree that there's a lot more emphasis these days on embodied carbon because of that, the perceived sense of urgency?
I think there's definitely more emphasis on it. I think that it's just that, yeah, part of it is like I mentioned it because the grid is electrifying. There's this thought that in the future that a lot of operational energy will be based on renewable energy. I think that's also a problem because solar panels also have embodied carbon.
Yes.
So I think like, we have to conserve energy rather than think, oh, operational energy is just going to not be an issue because we can rely on renewables. We still need to conserve energy in buildings. We still need to think about how to make more efficient buildings. And again, without compromising people's health. But being aware that everything also has material consequences is a good thing. Because again, if otherwise, like people will just say, okay, let's just make more fields of solar panels and we solve all of our carbon problems. And that's not right.
Right. Okay, let's switch back to humans. Several of your articles or the articles on your site, and I think you're involved with all of them, they speak to your work in characterizing radiant temperatures that occupants experience based on room design and factors related to room design. Now, a cursory reading on my part, it leads me to believe that the variations across the human body can be quite significant. Why is that, and what can we do about it?
Yes, so this was actually an important part of my PhD dissertation was actually understanding the specific impact of the radiant environment on your body. Meaning like, if you're sitting in a room, you're partially exposed to the window and there's sun coming in, maybe part of your body will heat up much more than another. Or if there's actually like a cold wall behind you, then your back will be much colder than your front, right? And we have thermoreceptors all over our skin, all over the surface of our body. So, our different body parts are also responding to these different temperatures. Now, this can either cause discomfort in certain situations, or it actually can cause pleasure. And I'll give you an example of that. It's what we call thermal anesthesia. For example, being sitting in a really cold place, like in Iceland, but in a hot spring. Your part of your body is submerged in something really hot, and then part of your body is exposed to really cold air, and that actually gives you a sensation of pleasure because it's this contrast that really, brings your thermal sensors to life, and you're really deriving joy out of that. So understanding these what we call like radiant asymmetries, where part of your body is being heated more than others. There's another level then of analyzing how that affects your comfort or discomfort. And there are actually models that are based on a kind of response of the sensors of the human body to understand that. And that's something we actually also published on, is like understanding how response to heat or being cold in one body part versus another would affect your thermal sensation. But I think it's interesting to just kind of break out of this idea that our body are like just these thermostats where you press on one temperature and then you're comfortable, and understand that we actually have all these thermal receptors, all these different parts of our body, and that the environment around us is going to affect it, because buildings are not these, completely perfect one temperature machines. And if we can understand that and work with that, then we can design better buildings.
I love that. Yeah, that was great. So we're starting to run out of time, but before we do that, I want to talk a little bit about style. Let's just talk about architecture for a minute. Do you still do any design, Dorit?
So because I like we had a quite a long conversation about
Yep.
how I build full scale
Yeah,
prototypes.
yeah.
And so I don't think about my research as separate from design. Most of the projects that I do research on, I end up like, spending together with the team members in my lab a lot of time on design, because this design is actually an integral part of what the research is, and it's going to impact everything about how it functions. So yeah, so like the materials that we use, the form, all of that is actually the research itself. So, I think of myself still definitely as a designer. It's just that I design systems that I also build and also test and also, make sure they function, which is actually more fun than for me than just being a designer that hands over a set of construction documents. Because here you actually have a responsibility that this thing actually works and that you're part of it, you're part of its life as it's operating as well.
Oh, what a wonderful answer. That was a great answer. Okay, it's the time in the show where I ask my $1,000,000 question. So there's a question that I ask every episode, and I ask our guests to answer it from whatever perspective they'd like. Dorit, what makes a great building?
Okay, so I would say that, you're talking about different perspectives. Even though, a lot of my research is as a building scientist, I would say that it's not necessarily the most comfortable building. There are many really good, like really good buildings that are comfortable. People enjoy being in them, they feel comfortable in them, but they are not necessarily great buildings. I would say that what makes a building a great building is that it makes a long lasting contribution to society or human culture. And, if I try to think of examples, when I was doing my master's, I studied also with a Colombian architect, Giancarlo Massanti. He took us to visit Medellin in Colombia, and he took us to visit some of the libraries. Some of them were built by himself, that were built in the informal settlements there. It was part of an initiative of the city to reactivate public spaces because people were scared to walk outside in public spaces. And I visited those libraries, and you see in Giancarlo Massanti's library, you see the children and mothers are playing outside, and this huge like rock-like building is standing on the side of the mountain, and it's this symbol for the community. And it brought all this life there where people are actually outdoors playing with children. That was a special moment for me. I think there are other types of meaningful contributions, like anything that from something that changes your whole experience of light, like in Louis Kahn's buildings or in the Alhambra or the Hagia Sophia, buildings that really you come out of and you feel like a changed person, and that's like over centuries. Or there are ones that change the way that we think about ground within architecture, like some of Sana's work. So yeah, I would say it's not necessarily the buildings that are the most neutral, like going back to this idea of thermal comfort, like needs to bring you to this like neutral zone. I would say that I much prefer the ones that really explore something more radical, and that with that exploration make a long lasting contribution.
Oh, wonderful. So before we go, is there anything that you'd like to announce? Any exciting announcements or anything you'd like to promote, Dorit?
Sure. So we are working on, currently, we received a Rumble Foundation grant together in collaboration with the architecture firm Henning Larsen. And we are working on building a new typology for cooling shelters. So this is going to be a full-scale pavilion that's going to be installed this summer in New York, and it's going to be open to public so people can come and actually experience this. And stay tuned for more details on the exact location. But yeah, we're going to employ radiant cooling panels there. We're going to employ this, we didn't get into this conversation, but it's membrane assisted radiant cooling panels that protect the cooling panel from humidity, so we can actually do this radiant cooling in hot and humid climates. Like the summer in New York or here in Philadelphia is very hot and humid.
Absolutely. I can't wait to hear more about that. Dorit, thank you so much for your time. It was an absolute pleasure chatting with you.
You too, Joe. Thank you.
Take care.
We hope you enjoyed this episode of Better Buildings for Humans. For more information on the world's best light diffusing and highly insulating glass glazing, please visit advancedglazings.com.